So in this video, we'll talk about the root test, which is pretty similar to the ratio test in flavor. So we're going to take the nth root of the absolute value of the nth term. We want to take the root of the positive values. And if that limit is L, and if that limit is less than 1, then the series converges absolutely. And remember that this means also that then the series converges. If the limit is more than 1, then the series will diverge. And if the limit is exactly 1, this test is not conclusive. So something we can say here is, something I'm going to point out, of course, is that in this case, we're also saying, including the case when the limit, when n goes to infinity, of the nth root of the nth term is infinity. So we're abusing a little bit the notation of saying if the L is more than 1, because in this case the limit doesn't exist, and I shouldn't be writing that term like that. But we include it in this case. Okay, so we're not going to prove all three. I'm going to show the proof of the first part. I'm going to assume, of course, that the limit when n goes to infinity of the absolute value of the nth term, the square nth root of that is a number L that is less than 1. So we're going to have the same situation as in the ratio test, where you have your number line and you have your number 1 somewhere, and your L is a number before it. So we said L is exactly less than 1, strictly less than 1. So we have this space, right, between L and 1. So I'm going to choose a number R, positive. We're going to pick a number R, positive, that is small enough such so that L plus R is still less than 1. Okay? So my R is right here. L plus R. It's right there. So this is what I'm calling R, right? So it really doesn't matter. I could call that number R in between. So because this is the limit, I'm assuming that the limit is L, right? So imagine I have my terms of this sequence, and the numbers of this sequence, right, the nth term of the nth root of the nth term, could be here, 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 here. Eventually, they had to go close to L and be only near here, right? So eventually, if I zoom in here, all my points are going to be on this side of this number, right? So this is the whole idea here, where I can say, so there is a number, I'm going to call it uppercase N, such that for all values of little n bigger than that value n, we will have that an, the nth root of the absolute value of an, is less than L plus R. This is the L plus R that I'm showing over there, right? So this means, and this is just because of the limit, right? And the limit, they're all going to get closer to L, so they have to be to the left of L plus R. So this means that if I can rewrite this like the absolute value of an is less than L plus R to the power of n. And the important part is that L plus R is still a number less than 1. Right? Okay. So that's all we need, because then we can write the series that I'm looking for of the an, I'm gonna find I'm gonna prove that it's absolutely convergent. So I put in absolute values. So if I add them all from 1 to infinity, it's the same than if I add the first, let's say n minus 1 terms of these, an, and then add the ones after that. I'm going to write here from n equals n up to infinity, right? Okay, but notice what's happening here. This is finite. I'm only adding a few terms. Well, n minus 1, but there are a finite number of them. So this is not going to blow up to infinity. And this is a geometric series, right? This is smaller. Sorry, it's smaller than a geometric series because this is a geometric series, L plus R to the n. This is smaller than, using this stuff that I have right here, this part is smaller than a geometric series, so this is bounded, right? So we're using a direct comparison test. This series is less than the series from L plus R to the n when n equals n to infinity, which is a geometric series with R less than 1. We call this less than 1. So it converges. So there you go. The series we're trying to find that converges is convergent because it's the sum of a finite number plus a series that converges. So we're done. Okay, so this is the proof of part 1. The part 2 is similar, and for part 3, the typical example is to look at these two series. This one diverges, while this one converges. And if you use the root test, and both of them, they give you 1, and one of them converges and one diverges. I'm going to basically use something about that one in my example. So let's go to an example. So my example is n squared over 2 to the n, and this is not a trivial example. It's not the first one that you would see probably in the book. It's a little bit more complicated, but it's not that hard. So I'm going to take, using the root, I'm going to use the root test. I'm going to take the limit when n goes to infinity of the nth root of the absolute values of the inside, but I'm not going to put the absolute values because I have only positive terms, right? I don't need the absolute values. So I need this. So this limit, I can rewrite it like this. It's n squared to the 1 over n divided by 2 to the n to the 1 over n. I wrote that middle step just to be a bit more careful. So I need to do this. N to the 1 over n. I'm going to write it backwards. Okay? And the bottom is just a 2. Right. So it all boils down to, can I find the limit when n goes to infinity of n to the 1 over n? And this is something that we did in the past when we did sequences. All I'm doing is find the sequence when n goes to infinity of n to the 1 over n. And for this one, it's a good review of techniques that we did in sequences. Is I can do, so to do that one, let me do it over here. I'm going to find if I'm going to call if an is n to the 1 over n. What we did, or we can do now, I think we did it before, is make bn the new sequence of the natural logs of these guys. That way, the bn, using the properties of logs, you can take the 1 over down, and it becomes this. So bn is really just ln of n divided by n. Okay. Now, this is one where I still cannot find the limit because the top goes to infinity, the bottom goes to infinity. But this is one where you can use L'Hopital if you think of them as a function. And we have a theorem that if you have a sequence defined as f of n, where f is a continuous function, then the limit of the sequence is the same as the limit of the function when n goes to infinity or x goes to infinity. So without writing out that step, I'm going to take the L'Hopital here with respect to n. So if you do the limit when n goes to infinity of bn, would be the limit when n goes to infinity of ln n over n. Here's where you're using L'Hopital's rule, and you can take the derivative of the top and the bottom, and this is 1 over n over 1, and there you go. So now that limit is easy to find, it's just a 0. right? Because the this numerator equals 0, and the denominator is going to stay at 1. So we're fine. Okay, so we found the limit of bn to be 0, right? But, cool, so now how do we find the limit of the an? Well, now we do the part of taking the function to a sequence again. Now we do e to the bn is really e to the ln of n to the 1 over n, right? But this is just an, right? Because here, in this side, e to the, oops, like wrong, e to the natural log of this would just cancel and give us n to the 1 over n, which is exactly what an was, right? Okay, so I have that e to the bn I can take this limit the same as taking this limit. This is the one I'm looking for. And e to the bn then we can do this part again where if you have a sequence, a function, continuous function, and the sequence is all the way in there, you can take the limit of the sequence and plug it in. The limit of the sequence is 0. So this becomes e to the 0 is the limit that we're looking for, which is 1. Oops, sorry. I want to write it backwards. I want to write the limit when n goes to infinity of my n is 1. Okay, so that's what I needed, because then up here, that's the one I found. So this is 1/2. Okay, so it's not a trivial example. If you remember that this limit is 1, you can just use it. But if you don't remember, then you have to go through this work that I did down here. That's justification. It's a good review of sequences for your final. Okay, so this is an example 1. I might have time in this video to do another example. If I don't rush it through, let's find out. So this is going to be a complicated, more complicated example. I think I'm not going to be able to finish it in the 2 minutes and a half that I have to finish this video, so I'll make another video with this example later tonight.